All right, so welcome back to another Math 230 and 231 GSG session. So for today's session, we'll be covering 14 point, oh, we'll cover 14.7 and 14.8 to finish off chapter 14. Yes, okay. All right, so yeah, looking at the Piazza page, someone requested to go over number 3 and number 10 for their homework. All right, so let's start off with number 3. So number 3 is actually based off 14.7. And so I'll pick a very similar question just with slightly different numbers. So you guys can try the actual homework problem by yourself. So that is going to be number 38 from the textbook. So this will correspond to number 3 from the homework. All right, so let's see what number 38 says. All right, so we're trying to find the absolute maximum and minimum value of f on the set D. All right, so for number 38, we're given f of x comma y, which is equal to x cubed minus 3x minus y cubed plus 12y. And it specifies that D is the quadrilateral at vertices -2, 3, 2, 3, 2, 2, and finally -2, -2 for the final vertex. All right, and again, we're trying to figure out what the absolute max and min are for f in the x comma y in D. Okay. All right, so let's see. So first of all, when you're dealing with these kind of questions, I would start off by figuring out what the critical points are. So I'll start off by finding what f sub x is, which is going to be 3x squared minus 3, and figuring out what f sub y is going to equal. In this case, it's going to be -3y squared plus 12. In order to find the critical points, we just set f sub x equals to 0 and f sub y equal to 0. And so for f sub x, we see, let me just draw a line. We can see for this equation on the left-hand side, we get that 3x squared is equal to 3, and hence this implies that x is equal to plus minus 1. And for f sub y, we get -3y squared, which is -12. And so this implies that y is equal to plus minus 2. All right, so we get the values for x and y. And so from this, we can say that our critical points are gonna be 1, 2, -1, -2, -1, 2, and -1, 2, and 1, -2. All right, so these are our 4 critical points. And now the next thing I would do, would also to draw out what the D actually represents. So let me just draw that out. So we should pull this down here. can say that we'll use black for the axis. Let's see. So we have this quadrilateral that looks something like, so this is 1 point right there, -2, 3. And then another point's going to be at 2, 3. The revert to C is going to be at 2, 2. And finally, -2, -2. All right, so this is what D actually looks like. And then this region is basically when we can say that this bound, everything inside this bound is continuous for the specific function you're given. So in this case, f of x, y. All right, so again, I'm just going to refer to this graph, and let's look at the critical points. So for 1, 2, we can clearly see that 1, 2 is going to be somewhere around here, right? So that's going to be critical point number 1. Now critical point number 2 is going to be at -1, -2, right there. And what you can notice, or what you probably can see, is that only 2 of the critical points are in the set D, or in the domain. Right? This is 3, and then 1, -2 is going to be right there. 4. Okay. So we can only say that 1 and 3 are in the set D. So we're not even going to consider options 2 and 4 as a possible max or min for f of x in D. Okay. So we figure out what the critical points are. So now the next thing we need to figure out is the extreme max and mins for the boundaries. Okay. So I'm going to split up this quadrilateral into 4 different segments. So I'll use green for that. So I'll split the left-hand side into I. The top segment of this quadrilateral is 2. And the right side is 3. And then finally, this one is 4. Okay, so we have that. And we're going to be referring back to this graph for the second part of this question. All right, so again, I'm just going to label my steps. So this was essentially step number 1, finding the critical points. Okay. All right, now the second thing I want to do is, as I mentioned, I'm going to find the extreme max and mins for the boundaries. Mins for boundaries. Okay. So again, so how we can do that is we can look into, so I'll start off with, let me just redraw this graph. Or this, let me just refer back to this graph right here. So I'll start off with line number 1, labeled it in green. All right, so line number 1. All right, so for line number 1, we can clearly see that the x value is always going to be at -2. So we can say that f of, so we can state that f, so we're looking into the function f of -2, y, right? And that is going to be equal to, so when x is -2, we get -8 minus, we get -8, yep, minus or plus 6. Well, let me just write down the function again. So what would be easier that way? X, y. That function is going to be x cubed minus 3x minus y cubed plus 12y. 12y. And so for line number 1, we again can say that x is equal to -2. So that's going to be -8 minus 3 minus 2 times -2 minus y cubed plus 12y. Right. Okay. So again, yep, that looks right. Okay. Okay, so we get, so simplifying this down, we get -y cubed plus 12y. Missing something? I think I'm missing something. It's 12. Oh, that's good. Okay. Oh, all right, give me a minute. Missing something. Yeah, I guess that's it. All right, yeah. Okay, yeah, so I copied the question incorrectly. So, okay, yeah, so we get -y cubed plus 12y minus 2. All right, so that's for line number 1. And for this, we can state that y is in between. So we start off at -2, and we're going, or we start off with, yeah, -2. Yep, all the way up till 3. So y starts from -2, and it goes all the way up to 3. All right. So we're given a cubic polynomial right here. And we're trying to figure out what my maximum min values are. So what I can do with this is I can figure out what my partial derivative is. So in order to find my max values for y, or my critical points for y. So I would take I'll take f sub y, which is going to be -3y squared plus 12, and then set it equal to 0. And in this case, I will actually get y is equal to plus minus 2. So we get critical points at y is equal to 2. But I'm not sure whether it's a max or a min, right? So what I can do is I can actually take my second partial, my second derivative in terms of y, which will be the same thing as -6y. And so when f of y is -2 comma, and when we're testing out y is equal to 2, we get that we get a negative number of -12. And so again, I'm just gonna label right here, first derivative and second derivative. And as covered in Calc 1, the second derivative basically implies its concavity, right? So with a negative value at that critical point, we can say that the curve is going to look something like this, right? Because it's going to concave down with a negative value of the second derivative. And hence, that's why for y is equal to 2, that is going to be a max value. Okay. So we obtain that at y is equal to 2. So let's put this up. So this is at y is equal to 2. This is going to be a max value, right? So if we actually figure out what the point is going to be, it's going to be the same thing as f of -2 comma 2, which is the same thing as -8 plus 24 minus 2, which is, we're doing that right. Okay, give me y is equal to 14. Yep. So this is going to equal to 14. All right, so that's for y is equal to 2. Now for y is equal to negative 2, basically essentially using the same equation. So I'm just going to plug this y equals to negative 2 back into the second derivative. So plugging in negative 2, we get negative, or f of y of negative 2 comma negative 2. We get negative 6 times negative 2, which is going to be positive 12. And hence concaves upwards, which means that this value at y equals negative 2 will be a minimum value, or a minimum critical point. Okay. So we can say that f of negative 2 comma negative 2 is going to be a minimum value at, let's see, so negative of negative 8, or yeah, negative 8 plus 12 times negative 2 minus 2, which is going to be 8 plus negative 24 minus 2. It's the same thing as negative 18. Okay. All right, so we got those 2 points for line 1. All right, so that's line 1. Check. Now let's look at line 2. I'm gonna do a bit long. So we do essentially the same thing for line 2. So for line 2, we get a y value of 3. So plugging that back in, we get f of x comma y value of 3, which is going to be equal to x cubed minus 3x minus 27 plus 36. Okay. All right, and then we want to do the same exact analysis. So for this case, we're given the y, so we want to find, again, we're given another polynomial, or specifically a cubic. And again, the domain for line 2 is going to be in between negative 2 and positive 2. Right, so negative 2 and positive 2. All right, so this cubic's going to look something like this. Okay, so again, finding the derivative. So f prime x comma 3 is going to be the same thing as 3x squared minus 3. Okay, and sorry, yeah, that's 3, which is equal to 0. And so my critical points are gonna be at x is equal to plus minus 1. All right, so my critical points is when x is equal to plus or minus 1. And what I want to do next is, again, these are the critical points, or a critical value for the x, point value of x. Now I can take the second derivative and see whether it concaves up or downwards. Right, taking the second derivative, I get a 6x. And so for x is equal to positive 1, I get that, for positive 1, I get that f double prime of 1 comma 3, which is equal to 6. Hence, this implies that at x is equal to 1, comma, it's going to be a minimum. While at x is equal to negative 1, f double prime negative 1 comma 3, which is equal to negative 6. So this implies that at x is equal to negative 1, it's going to be a maximum value, right? Because these are the only 2 critical points of the polynomial. Now, okay. So let's see. So that's for line 2. Okay. Line 2. So, yep, line 2. Okay. All right, so let's see. So at x equals 1, so at f 1, comma 3, that is equal to 1 minus 3 plus 9. Yeah, plus 9, which is equal to 7. While the maximum value is going to be f double prime negative 1, comma 3, or f1, comma 3, sorry. F of 1, comma 3, which is going to be the same thing as negative 1, comma 3 is going to be the same thing as negative 1, comma 3, so negative 1 plus 3 plus 9, which is 11. Okay. So we get, yep, a minimum value of 7 and a maximum value of 11. Okay, so that is line 2. Okay, so now that's line 2. And let's look at line 3 right now. Okay, so again, we do the same exact procedure. So for line 3, we have that at line 3, we have a domain from y is equal to 3 to y is equal to 2. All right, so it's going to be in between 2 and 3. And then we can say that the x value is going to be a 2. All right, so we have f of 2 comma y. F of 2 comma y, which is equal to x cubed, so 8 minus 6. 8 minus 6 plus minus y cubed plus 12y, minus y cubed plus 12y. Minus y cubed plus 12y. All right, so we have that function right there. And then we have the domain from 2 till 3. All right, so again, find the critical points for this equation right here. So we get negative 3y squared plus 12. And so again, y is going to be plus or minus 2. Right? So based off this, since y can only be positive 2, right? Since you're looking at y is equal to 2 and y is equal to negative 2, y equals to negative 2 isn't going to be part of this domain right here. Right? So we're not even going to consider y is equal to negative 2. So what we can do is we can determine whether this is a max or a min value, right? Max or min. So we can take the second derivative, y, which is negative 6y, and then plug in 2. And if you plug in 2 into that, we get negative 6 times 2, which is negative 12. And hence, at y is equal to 2, this is actually going to be a maximum value, right? Based off the fact that it concaves downwards. All right, so we can say that f of 2 comma 2 is going to be a maximum value at 2 minus 2 cubed plus 24. And that's the same thing as 2 minus 8 plus 24. So minus 6, that'll be 18. Okay. All right, so that's the maximum value. And now we're trying to find another minimum. So we need to also find its minimum. So for its minimum, since this function is continuous, right, we can say for a cubic function, after reaching the max point, it's going to go downwards, right? So we can, this implies that at y is equal to 3, this value right here is going to be a minimum value. So we can try to figure that out. So f of 2 comma 3 is the same thing as 2 minus 27 plus 36, which is the same thing as 9 plus 2, which is 11. Okay. Yep. And that's going to be the minimum value right there. So 11 is going to be the minimum value for line 3, and 18 is going to be the maximum value for line 3. Okay, and then the last line in the graph. All right, so we have this vertice of -2, -2, and we have that vertice of 2, 2. So we can see that this line right here, since it's going from -2 to -2, -2 to 2, +2, we can say this has a slope of 1, and we can say that this line, line 4, is actually going to be, so line 4 is actually gonna be y is equal to x. Okay. All right. So, and then we can also say that it goes from, yeah, we can also say that the domain for x is going to be from -2 till +2. Okay. -2 is going to be less than or equal to x is going to be less than or equal to 2. Right. And based off this right here, we can state that f(x, x) is actually going to be the same thing as 8 or x, x, right? Because we're substituting in y as x. We can say that yeah, f(x, x) is the same thing as 9x. Okay, this is the same thing as 9x. All right, so now looking at this question right here, yeah, since 9x is going to be a linear curve that slopes upwards, we can say that the max value is going to be when x is equal to 2, and the min value is going to be when x is equal to -2. And so the max value is actually going to be f(2, 2), which is the same thing as 18, since f(x, x) is 9x. And then the minimum value is actually going to be -2, -2, right? And that's going to be -18. Okay. So now the last thing we need to do is we need to compare all the different values we got. So, all right, so let's try and write it all down to you in a new page. All right, so we start off with the critical points. So f of, I think it was 1, 2, 1, 2, and -1, 2. 1, 2, f -1, 2. Now for line 1, we saw that we have a max value of 2 and a min value, or a max value of 14 and a minimum value of -18. Okay. So for line 2, or line 1, sorry. Yeah, this is line 1 is going to be a max value. So for line 1, we have a max value of 14 and a minimum value of -18. Now for line 2, the max value and the min value is, let's see, 2. So we have a min value of 7 and a max value of 11. Min value of 7, max value of 11. Now for line 3, we have a max value. Line 3, we have a max value of 18 and a min value of 11. 11. Now for line 4, which is the last line that we just figured out, we have a max of 18 and a minimum of 18, -18. All right. So going back to the, let's just try to figure out the critical points first. So f(1, 2) is actually going to be Did we figure that out in the beginning? No, I guess we didn't. Okay, let me just write that down then. X cubed minus, so 1 cubed minus 3 is 1. 3 times 1 minus y cubed plus 12y. All right, minus 2q plus 12 times 2. All right, that's going to be -1 minus 3 times -1 minus 2q plus 12 times 2. All right, so we get 1 minus 3 minus 2 minus 8, which is minus 10, and then minus 10 plus 24 is going to be 14. And then we have minus 1 plus 3, which is 2. 2 minus 8 is -6, and 24 minus 6 is -18. Okay. So based off all these values, we see that -18 is going to be my absolute minimum. And my absolute maximum is actually going to be positive 18 right there from line 3. All right, so yeah, I'm gonna write down the different steps that we just went over for this question. Okay, yeah, it was quite a lengthy process. All right, so for, yeah, number 38 process. I guess the first step I would do is draw the specified set for D. All right, specified set D. So that's the first thing I would do. So this, again, comes from like the vertices that they give us and what kind of shape it is. So yeah. And then the second thing I would do is I would find out what my critical points are. So after finding my critical points, I want to see which critical points are in the vertices or in the set D. Okay, that's the next thing I want to check. And then from that, what I can do is I can find or evaluate fx comma y based off critical points. All right. And then the third thing actually relates back to your given specified set of D, or the given set D. All right. So for the third step, what I would do is I would chunk up the different borders to different segments. All right. So split the borders to different segments. And then from that, what I can do is that, let's see what we went over. So we tried to figure out the maximum and minimum values, right? So from, splitting the borders to different segments, find respective functions for different segments, right? Yeah, the next thing we figured out was our functions. So like for line, let's say line number 1 over here, right? We noticed that line number 1 was only when x was equal to -2. So by plugging in x equals -2, we found a function in terms of y, right? And now from that, what we can do is we can find our max and min values is for the respective functions. Okay. Right. So we found each respective max and min values from all the different borders or the different segments of the borders. And then finally, the last step you need to take is you need to compare different max and min values to find the absolute max or min. Okay. All right. And yeah, that should that should help guide you through number 3 from the homework. Okay. All right. Now the next question that we're going to cover is actually number 10 from the homework. So again, this is from the Piazza post. So number 10 corresponds to number 5 from 14.8. Yeah. So we'll cover that right now. Okay, so let's see number 5. Okay. So again, for number 5, we're trying to find what the absolute max and min values are, but we're going to use a different approach by using the Lagrange multiplier method. So let's go through that. So for fx comma y, in this question we're given xy, and then an additional constraint that they give us is that 4x squared plus y squared is equal to 8. Okay, let's look at this. All right, one thing you need to refer to when doing the Lagrange multiplier method is that we can say that the gradient vector f x comma y is equal to lambda g x comma y, or the gradient vector g x comma y, while we can say that g x comma y is equal to some constant k. Okay. All right, so let's look at this. All right, so what I would do first for these kind of questions is I would find out what my value for f is, and the gradient vector f and the gradient vector g multiplied by lambda. All right, so let's try to find this out. So gradient vector f is actually going to be, so for this case, it's actually going to be y comma x, and then the gradient vector multiplied by lambda of g is going to be, so in this case, it's going to be 8 lambda x, yes, 8 lambda x, comma 2 y, 2 lambda y. Okay. Okay. All right, and these two functions right here, they just come from the constraint right there. All right, and then what we can do next is we can actually set each respective component between each other. So we can say that y is equal to, y is equal to, yeah, y is equal to 8 lambda x. Sorry, there's something going on. We can say that and we can say that x is equal to 2 lambda y, while also including this equation here. Now, the next thing, or the next procedure, or the next step for this procedure is to solve this system of equation. And there are a couple ways of doing this, but what I would do is I would start off by looking at these two equations. And what I can see is that lambda is equal to y over 8x, which is also equal to x over 2y, right? Yes, that looks right. And then from that if y, we can have that lambda is equal to y over 8x. And this actually also implies, we can actually see this because we have y in the denominator for each fraction. This also implies that y cannot equal to 0 and x actually cannot equal to 0, right? Because if we do that, then it's going to be, we're dividing by 0, and that cannot happen. All right, so now what we can do from this is we can start by cross multiplying these two fractions. So I'm just going to actually focus at y over 8x, which is equal to x over 2y. Let's see, yeah, by cross multiplying we get 2y squared, which is equal to 8x squared. And this can be reduced to y squared, which is equal to, 4x squared. All right, then I can actually use this now, this equation that we deduced, and plug it into this constraint equation right there. So from this, I get 4x squared plus, should be 4x squared? Yeah, 4x squared, which is equal to 8. And then from that, I can actually solve for x. So in this case, we have that 8x squared is equal to 8, and hence x is equal to plus minus 1. That's going to be our value for x. And then for y, we can just plug it back in. We can just plug it back into this equation. So we have 4 times 1 squared plus y squared plus 8. Or y squared is equal to 8, sorry. Right? And then we can see that y squared is equal to 2, and hence y is equal to plus minus 2. All right. So this is actually going to represent our critical points or possible extreme values, right? So we can check that f has the extreme values at 1 comma plus minus 2 and negative 1 comma so negative 2. I guess, all right, so let's see, f1 comma 2, f negative 1 comma 2, f1 comma negative 2, and finally f negative 1 comma negative 2. All right, so let's start evaluating these questions. And so at f1 comma 2, we get 2. Right. At f negative 1, and it's just going to alternate. So it's going to be negative 2. It's going to be negative 2 since our function fx comma y is the same thing as xy. Okay. And positive 2. All right, so we can say that our absolute minimum is going to be 2, while our absolute maximum is going to be negative 2. Okay. Well, that should be it for number 10 from the homework. All right. And I'll actually do one more that's going to be similar to number 10. All right. So for number 10, we've dealt with 2 variables, right? A function f with 2 variables and function g with 2 variables. Now for number 7 in 14.8, introduced to a function f in terms of x, y, z. So let's go through that problem right there. So 14.8, number 7. Okay. So we have that f x comma y comma z is equal to 6x plus 6y plus 5z. And then we have the constraint 3x squared plus 3y squared plus 5z squared, which is equal to 29. All right, and then we have, again, the first thing you want to do is, so this is the first step, find the gradient vector of f. So gradient vector of f is going to be, 6 comma 6 comma 5. Yes. All right, and then the second thing I want to do is find the gradient vector of g multiplied by lambda, which is going to be 6 lambda 6 x comma lambda 6y comma lambda 10z, right? Because again, this is going to be g sub x, this is g sub y, while this is g sub z. All right, so now we have the gradient vector of f and g. Now we can set them equal to each other. So we have 6 is equal to lambda 6x. Then we have 6 is equal to lambda 6y. And finally, we have 5 is equal to lambda 10z. And then we have the equation 3x squared plus 3y squared plus 5z squared is equal to 29. And then all we're trying to do is solve this system of equations. All right, so what I can set first is I can say that lambda is actually equal to 1 over x, which is equal to 1 over y, and that is finally going to equal to 1 over 2z, yes. All right, so now let's look at a constraint right here. Oh, okay, so we're given x, y, z. Oh, actually, what we can do is we can plug in values of lambda in terms of x, y, and z. So I'm just going to rewrite this. So this can be rewritten as x is equal to 1 over lambda, comma, y is equal to 1 over lambda. And finally, z is equal to 1 over 2 lambda, right? And what I can do is I can plug this back into this equation. So I get 3 over 1 over lambda squared, right? Plus 1 over lambda squared, and plus 1 over 2 lambda squared, which is equal to 29. All right, let's see. Yeah, we can definitely simplify this out. We can take 3 plus 5 over 4, multiply that by 1 over lambda squared, right? We're factoring out a 1 over lambda squared, and then setting that equal to 29. Let's see if that simplifies it out. So that'll be 3 plus 3 plus 5 over 4, so that's 6, 24. Oh, that's 29 over 4. Perfect. 29 over 4 times 1 over lambda squared, which is equal to 29. And from this, let me pull up a new whiteboard. So we have 29 over 4 times 1 over lambda squared, which is equal to 29. And so 1 over lambda squared is equal to 4. And lambda is equal to plus minus 1/2. There you go. Okay, so lambda is plus minus 1/2 is equal to plus minus 1/2. Now we're not done yet. We have to find our values in terms of x, y, and z, right? So just plugging it back into that equation, x over 1 over lambda, y is equal to 1 over lambda, finally z is equal to 1 over 2 lambda. We get that x is equal to plus minus 2, y is equal to plus minus 2, and z is equal to plus minus 2. All right. And then now finally, we're trying to figure out what our maximum or absolute maximum, absolute minimum are. Now going back to our function, we have that f(x, y, z) is equal to 6x plus 6y plus 5z. All right. Now what you notice is that if you plug in all positive values for x, y, z, we'll get the highest possible value that can be obtained from this set of numbers. Right? Oh wait, sorry. Z is not plus minus 2, is it? It's, yeah, z is plus minus 1. I am sorry. Yep. Plus minus 1. Yes, that looks, yep, because 2 times a half is 1. Okay, perfect. So we get that. And now if we plug in all negative values, that's definitely going to be our minimum value. Just because that all this is just a summation of all positive integers. Okay, so we have that a max value is going to be when f of x is equal to 2, comma y is equal to 2, and z is equal to 1. So that's going to be 12 plus 12 plus 5. That's 29. And we have a minimum value or absolute max, sorry, absolute min of f of negative 2, comma negative 2, comma negative 1, which is negative 29. Right? So that is basically another question for solving absolute max or finding absolute max and mins using the Lagrange multiplier method. Okay, and yeah, I think I'll end off this session here. Yeah, that was just 2 different ways of finding absolute maximum and minimums. Okay. All right, thank you for tuning in, and I'll see you next week.